All right, so again, this is one of those things where now that we have the system linearized, it is possible to solve this system using conventional methods, Laplace transforms, or eigenvalues and eigenvectors, and it would not have been possible otherwise because of the function of the dependent variable here of sine of theta. So the whole purpose here was we were able to eliminate that from the process. So now let's do a comparison of these two models, and so the idea here again is that if I pick an initial condition that lies close to the close to one of the equilibrium points, and I've linearized around that equilibrium point, that the behavior of the function should be this very similar around that equilibrium point. So if you look at this phase plane and this phase plane for an initial condition that's the same initial condition just on the original function where d theta dt equals v versus dv dt equals negative v minus sine of theta, and then the linearized version d theta dt equals v and dv dt equals 1 theta minus v. Okay, so there is of course a little bit of similarity right in that region, very close to that initial point, but of course as the value of, in this case, t gets further away from theta, gets further away from pi, then the behavior becomes more erratic and varies more greatly. So if I compare the linearized pendulum versus non-linearized pendulum over a short period of time, I can see that the behavior is roughly the same. That is, the angle begins increasing from pi to beyond pi, and of course that behavior is a little bit different. This of course is a different time interval, so from 0 to 1 here we notice that there's actually less change than there is from 0 to 1 here, and so the idea is that we just get the same qualitative behavior in that region. So really, this is a more formal statement of the linearization theorem. Suppose that the y0 vector is an equilibrium point. So for us, y0 is the vector consisting of, in our case, let's see, pi 0 for the nonlinear autonomous system, then where dy dt equals is a function of y. So that instead of using x, they're using y here. So we could always change this back to x. And let dy dt equal the Jacobian times the variable vector. Let that be the corresponding linearized system at the equilibrium point. If the following conditions hold, the determinant of the Jacobian is not 0, that written det j, and the determinant of a matrix, of a 2x2 matrix with elements a, b, c, d, the determinant of that is the difference between the cross products a times d minus b times c. Okay, we won't discuss what exactly that means in the context, but that would be the determinant. So if the determinant is not 0, so let's see what ours is. Here's our matrix, and the determinant of that would be 0 times negative 1, which is 0, minus 1 times 1, which comes out to be negative 1. So check, we've accomplished that. The determinant of j is not 0, and the eigenvalues of j are not purely imaginary. Then the solution curves of the nonlinear system near that point behave in the same qualitative way. And note that that's a very vague statement. We don't really know what it means to say the same qualitative way. The qualities are similar as the solution curves of the linear system. So if we won't talk about computing the eigenvalues here, but if I want to know what the eigenvalues of this matrix 0, 1, 1, negative 1 are, I can use a computer system. Here's a link to that computer system, and I have it entered here. I can compute eigenvalues and eigenvectors, compute them, and all I'm just going to make sure is that they're not purely imaginary. Okay, well, first of all, both of these eigenvalues that come out here are both real, and therefore I've satisfied the premise of the linearization theorem, and thus it makes sense that the qualitative behavior is the same. Now, quantitatively, they differ greatly, right? Because qualitatively, we see a concave up segment for representing how theta changes over time, and qualitative up segment for how theta changes over time. However, quantitatively, the values along the value of theta, the angle of the pendulum at any given time, is different than it is in the linearized system. So gives us a good estimate. It's an approximation approach, and it's a useful approximation approach, but it has much to be desired in the way of giving us exact behavior.